Okay, it's 11. I want to get started right away today. So hopefully they're done outside pretty soon. We ended here. I do have some announcements before we go through this question. Just that your chapter 3, part 2 Achieve is due Monday. Another reminder for that. The McLean lecture hosted by the Chemistry Club is this Friday. In this room at 6:30 p.m. So I encourage you all to attend. I posted the flyer in a Blackboard announcement yesterday. And then Professor Cunningham teaches one of the sections of 1070, and she's going to have office hours for a number of general chemistry classes, and you're welcome to attend those office hours and ask her questions as well. So they are 2 to 4 p.m. Wednesday and Friday in C117. That's just right across the hall here. So feel free to also use those office hours to your advantage. I'll have your exams on Friday. I don't have them today. Yeah.
I was just going to say, any benefit
What'd you say? You benefit from learning about what this professor has to talk about. No, I don't have extra credit, but that doesn't mean that you shouldn't attend. So I mentioned he's a professor in pharmacy, and so I believe he's going to talk about his journey through his career. Yeah. Okay. So we ended with some time working on this question, so I'm just going to go ahead and go through it. So we have ammonium nitrate, which is a fertilizer. We have a 1 pound bag, and we want to know how many moles of nitrogen atoms are in this bag and how many atoms that is. So we start with the measurement that's provided. We start with a 1 pound bag. And if we want to end up in units of moles, we need to first convert to grams, and then we can always convert grams to moles. So we have to convert pounds to grams using the conversion that's provided. Now we're in grams of ammonium nitrate. We can convert to moles of ammonium nitrate using its molar mass. Now we don't know the molar mass, so we need to find the molar mass of NH4NO3. And to do this, we add up the atomic masses of each atom, multiplying by the number of each atom present in the compound. Do we have a question in there? Okay, let's remember to quiet down while I'm talking. Thank you. So we have 2 nitrogens. So I'm just going to go ahead and write in the atomic mass of nitrogen times 2. We have 4 hydrogens, so 4 times the atomic mass of hydrogen. And we have 3 oxygen, so 3 times the atomic mass of oxygen. We get a molar mass of ammonium nitrate of 180.052 grams per mole. So now we can plug that into that fraction there. Yes. You have 80? So do I. Yep. Thank you for that catch. Okay, so that's the molar mass. There's a lot of chatting. You all know how I feel about that, so please quiet down. Thank you. We have the molar mass of ammonium nitrate. So we can convert to moles of ammonium nitrate. And then the question is about moles of nitrogen atoms. We have, in every 1 mole of ammonium nitrate, we have 2 nitrogen atoms. So we have 2 moles of nitrogen in every 1 mole of NH4 NO3, because there's 1 nitrogen in NH4, 1 nitrogen in NO3. So now we've converted to moles of nitrogen, and you should get 11.3 moles of nitrogen. And then once we have moles of nitrogen, the second question is how many atoms is this? We can convert that amount of moles to atoms just by using Avogadro's number, so 6.022 times 10 to the 23rd atoms per mole. This is 6.80 times 10 to the 24th atoms of nitrogen. I went through that fast. I kind of assumed that you all had finished it in the last few minutes of class, but do y'all have questions? Okay. So when we have the chemical formula of a compound, we can determine the moles of each atom as long as we have the mass. If we have the mass of different atoms, we can determine the amount present. We can determine a molecule's molecular or chemical formula by first determining its mass percent composition. So the percent composition of each atom present in a compound. We can use that to determine its empirical formula. And then we can use its molar mass to go from empirical formula to its molecular formula. So these are the next 2 sections of the book. First one is percent composition, just a couple of slides. That leads into empirical formulas, which we will certainly talk about what that means. So percent composition is, we've actually kind of already done this, where if we have a certain mass of a compound, if it's a specific compound, there is a percent composition of each atom in that compound that's consistent no matter how much of that compound is present. The percentage is always consistent. So we'll calculate percent composition just using some mass information. So the mass percent composition, that's what this blank is here. So the mass percent composition is the mass of each element present in 100 grams of a compound. We can calculate the mass percent composition by dividing the mass of each element by the total mass and then multiplying by 100. So this example here, we've seen this example of water in the past. We have 18.02 grams of water, and we should have 16 grams of oxygen present. If we multiply that by 100%, we have 88.81% oxygen. Looking at this first bullet point, in water, if we have 100 grams of water, then we have 88.81 grams of oxygen. So that's what that first bullet point is saying, is that if we have a mass percent composition, that is also the mass of that element in 100 grams of the compound. We can do the same thing for hydrogen and get the percent composition of hydrogen. And determining the mass percent of each element in a compound is also described as elemental analysis. So you just might see that term, just know we're talking about mass percent there. So let's just do this example with copper sulfate pentahydrate. We're going to use mass percentages to do this calculation to determine grams of copper and 20 grams of copper sulfate pentahydrate. There are multiple ways to reach the answer of the question that is asked here. We're going to go through the process of percent composition, and then I'll verbally describe a more direct way to calculate this amount. But the purpose of using percent composition is to lead us into the next section. So if we have copper sulfate pentahydrate, and we want to find the mass percent of copper in copper sulfate pentahydrate, we use the molar mass of the full compound and the molar mass of copper. So we have to calculate first the molar mass of the compound. We have one copper atom, so 1 times the molar mass of copper. One sulfur atom, 1 times the molar mass of sulfur. And we have 9 oxygen atoms. We have 4 in copper sulfate and then 5 in the pentahydrate. So 9 times the molar mass of oxygen, and then 10 times the molar mass of hydrogen. We have 10 hydrogens in this compound. This is, again, to calculate the molar mass of that compound. So this is 1 times the molar mass of copper is 63.456 grams per mole. 1 times the molar mass of sulfur is 32.06 grams per mole. 9 times the molar mass of oxygen is 143.99. And then 10 times the molar mass of hydrogen is 10.08 grams per mole. This gives us a total molar mass of 249.68 grams per mole. Okay, so we've used the periodic table to calculate the molar mass of the full compound, and then to find the percent composition of copper in this compound by mass, we divide the mass of copper in the compound, 63.456, divided by the total molar mass. And then times 100, and this is 25.451% copper. So this is the percent of copper by mass in every copper sulfate pentahydrate compound. It's always 25.451%. So if we have a 20-gram sample of copper sulfate pentahydrate, 25.451% of that is copper, the weight of copper. So we can find the grams of copper in 20 grams of the full compound by taking 20 grams of copper sulfate pentahydrate and multiply by this percentage. When we multiply by a percentage, though, we need to convert it to a decimal. Out of 100, so this is 25.451 grams of copper out of 100 grams of the full compound. So we convert that to the decimal there, and this gives us 5.09 grams of copper. In 20 grams of copper sulfate pentahydrate. So as long as you know as long as you can find the mass percent of each atom in a compound, then if you have any amount of that full compound, you can calculate how much of each element is present in that provided mass. So in this case, in the 20 grams. If we followed the process that we followed in previous examples on Monday, we could also calculate the same number by saying we have 20 grams of copper sulfate, use the molar mass to convert to moles of copper sulfate, and then we say we have 1 mole of copper for every 1 mole of copper sulfate, and that would give, and then convert to grams of copper, and that gives us the same number. So 2 different ways to calculate this final answer. This process is just to show that if we have the mass percent, then we can also calculate the amount of grams of an atom. We can go back to find the moles, etc. So we'll use that when we're working on empirical formulas, which is the next section. Questions before I move on? Okay. So we will use percent composition or other mass ratio data to determine the empirical formula of a compound. And the empirical formula is the chemical formula for a compound that uses the smallest whole number ratio of the atoms in a compound. So for example, if we have an empirical compound that's CH4O, that means for every 1 carbon atom, we have 4 hydrogens and 1 oxygen. If that's the empirical formula, the actual formula will either be the same as the empirical formula or some whole number multiple of the empirical formula. We need more data, which we will eventually get to this example, to determine if the empirical formula is the molecular formula or not. But as an example, if we have an empirical formula, CH4O, that could mean that the actual molecular formula is C2H8O2. So the atoms are still in the same ratio, but there are more of each atom, so 2 times the number of each atom in that molecule. It could be C3H12O3, etc. So some whole number or multiple of the empirical formula. Okay. let's say, now let's use the information about mass that's present to determine an empirical formula. If we have, let's say, a 20-gram sample of an unknown compound, and a chemical analysis indicated that it has 1.34 grams of hydrogen, 8 grams of carbon, and 10.7 grams of oxygen. We can use this information to determine its empirical formula, but remember that in empirical formula, these subscripts here, these are molar subscripts. So for every 3 moles of carbon, there's 12 moles of hydrogen, 3 moles of oxygen. So if that's the formula. So we can't go directly from grams of each atom to its empirical formula. We have to convert grams of each atom to moles of each atom. So if we have 1.34 grams of hydrogen, we need to know moles of hydrogen that's present in the sample. And so we use the molar mass of hydrogen from the periodic table. For every 1 mole of hydrogen, we have 1.008 grams of hydrogen. In this, doing this conversion, we have 1.33 moles of hydrogen. Oh, we do the same thing for carbon and oxygen. So 8 grams of carbon times or divided by its molar mass and then same thing for oxygen, 10.7 grams of oxygen divided by molar mass, 1 mole over 15.999 grams. And that's 0.669 moles of oxygen. So what we've calculated here is the molar ratio of all 3 of these atoms in this unknown compound. So we could say the formula, now we haven't talked about this, but if we have carbon and hydrogen in a formula, we list carbon first. So we could say the formula is C 0.666, H 1.33, O 0.669. That represents the molar ratio of all 3 of these atoms in the compound. But as you all know, we don't use decimals when we're writing out a formula. So we need to keep this ratio, but we want whole numbers as the subscripts here. So what we do to get a whole number is divide by the lowest number that's there. So we divide by 0.666 for each number. Since we're dividing by the same number, we're not changing the ratio. We're just simplifying the numbers that are there. So this gives us, if we simplify the fractions, C1, H2, O1. If you simplify this fraction, I think it's 0.999. At that point, we can round up to 1. But one more thing, we never use subscript of 1 when we're writing out a formula. So we simplify this one more time to CH2O. And that's the empirical formula of this compound. Yeah.
So you're always able to round
For like the 0.99, is that what you mean? So we're going to go through an example where the number we get is 0.96. That one we don't round. So if it's like 0.001 away, that's fine. But you'll see, once you go through examples, you'll see there'll be like let's say 1.4999. We can round that to 1.5. It'll be very close to the whole number. Okay, so the next slide has basically all of these steps written out, where I'll go through these steps and do another example as we go through them. So our example is that we have 39.2 grams of phosphorus and 60.8 grams of sulfur in an unknown compound. We want to determine the empirical formula. We're following the same steps as we did on the last slide. So the first step is to convert the mass of each element to moles of each element using molar mass. So if we have 39.2 grams of phosphorus, multiply by its molar mass from the periodic table, which is 30.974. That's 1.266 moles of phosphorus. Now we do the same thing for sulfur. Now this first step gives us the molar ratio between the two compounds. So we have the molar ratio here, but in the next step we need to simplify it to whole numbers by dividing by the smaller number. So if we write this formula as phosphorus 1.266, sulfur 1.896, we then divide the subscripts by the lower number. And then doing this division, we get P1 sulfur 1.5. Yeah. Keeping 3 decimals is sufficient, and I suppose that does follow sig figs, but keeping 3 decimals or 3 places past the decimal is sufficient for doing the rest of the calculations. You definitely don't want to round 1 to like 1 past the decimal, or maybe even 2, because I think that could mess up the ratio when we need to divide. Okay, so after step 2, in the last example we were done here, we had whole numbers for the subscripts, but here we still don't have a whole number. So if you get to this step and you don't have whole number subscripts, we can't divide by the lowest number again, because the lowest number is 1. We'd get the same molar ratio here. So then we move on to step 3. So if the subscripts are still not whole numbers at this point, convert to whole numbers by multiplying the subscripts by the same small whole number. Usually we're multiplying by 2, 3, or 4, and it's whatever number is going to then give you whole number subscripts. So in the lowest number. So in this case, if we multiply by 2, this will be 3, that will be 2. So 2 works. Multiply by 2 for each subscript. So I'll say P1 times 2, S 1.5 times 2, and that gives us P2 S3. And now this is our empirical formula, P2 S3. Yes. Yes, in a moment. Other questions though? Okay, I have an iClicker. It's not in your slides, but it's finding the empirical formula, essentially doing step 2. And I'll go back to the slide. Be careful, B and C are very close. So be careful if you're picking B or C. If you have questions. Also, if you finish in 2 slides, there's another example question. You can get started on that. Let's say 30 seconds. Ten seconds. Okay. Ending it here. Okay, so B and C were the 2 answers that were selected. They are very similar, and I did that for a reason. When we're writing empirical formulas, you not include the 1s. So you remove the 1s, it would be CH4 0 as that empirical formula. And what we do here is we divide by the lowest number, 0.25. That gives us C1H4O2 simplified to CH4O2. So when we talk about finding the formula of an ionic compound, most ionic compounds are just identified by their empirical formulas. And that's because ionic compounds are repeating patterns of ions. So we've seen sodium chloride as an ionic compound a lot, magnesium bromide, ammonium nitrate, which we just did that example with. They're the simplest ratio. If we were to find empirical formulas, this is what the empirical formula would be. And you can assume if you have an ionic compound, its empirical formula is the formula of the ionic compound. Remember when we looked at the particle picture of sodium chloride? It was a cube lattice structure with a bunch of repeating units of sodium and chlorine atoms. Its simplified version is the empirical formula, sodium chloride. So just a note about ionic compounds. Then let's do another example. So this is an ibuprofen example, active ingredient in a lot of over-the-counter pain relievers. So let's say an analysis says we have 75.7% carbon, 8.8% hydrogen, 15.5% oxygen, and we want to determine its empirical formula. When we're provided mass percentages and not actual masses, we can just assume, you can assume any amount of the full compound that's present, but it's easiest to assume 100 grams because then you have you have 75.7% carbon, you have 75.7 grams of carbon in 100 grams of the full compound. So we can assume 100 grams of ibuprofen. Now we follow the same process that we did in the previous example. So we convert grams of carbon to moles of carbon. We convert grams of hydrogen to moles of hydrogen using its molar mass from the periodic table. Now we do the same thing for oxygen. And we get the molar ratio of all three atoms in ibuprofen. So this is 6.303 mole carbon, 8.730 mole hydrogen, and 0.968 mole oxygen. This is an example where we have a decimal that's close to a whole number, but not close enough. So 0.999 we assume is 1, we can round to 1. 0.968 we should keep as 0.968. Rounding that up would mess up the molar ratio. It's too far away from 1. Okay, so we have the molar ratio. We can put this into the formula C 6.303, H 8.730, O 0.968. Here's another clue that we shouldn't round this number. This is the lowest number of the three. And if we rounded this to 1 and divided by the lowest number, we have some funky decimals there. So we keep as 0.968, divide each of these by 0.968 because that's the lowest number. This provides C 6.5 H9O1. I don't have written down what these fractions are, but it's probably not exactly 9 or probably not 6.5. But if you have the numbers, that'll give you an idea of what you can round. Okay, so we don't have whole numbers for every atom. We have a 6.5 there, so we need to multiply again by a small number. We can multiply by 2 and get all whole numbers. So I'm just going to write times 2 in parentheses there, and that will give us the empirical formula C13 H18 O2. Yes.
What's the molar mass just there? Like you didn't have to use it?
We will come back to the molar mass. Yeah, good question. So for finding the empirical formula, you don't need the molar mass. We're now going on to molecular formulas. And to determine the molecular formula, you do need the molar mass. Questions about this process, though, before we move on? Yes.
Why did you decide to keep never like 75.7%, so just do 75.7 instead of dividing by 100. I don't know.
Yeah, so if you're just given percentages, you can assume any amount of the compound, but I find it easiest to assume 100 grams is total. So if you have 75.7% of carbon in 100 grams, then then you have 75.7 grams of carbon.
And you don't get to try to get rid of it.
No, I essentially did that without showing the work. Okay, so now this is the empirical formula. This last section, or not the last section, second to last section, will determine the molecular formula from its percent composition and molar mass data or empirical formula. So going back to this ibuprofen example, we determine the empirical formula is C13H18O2. Using this information that we haven't used yet, its molar mass is less than 210 grams per mole. How could we determine if this empirical formula is the molecular formula? Yeah, so we find the molar mass of the empirical formula. If it's just less than 210 grams, then that's also the molecular formula. If it's 100 grams, then we don't have the empirical formula. We would need to multiply the subscripts by some factor to end up with closer to 210 grams. So go ahead and calculate the molar mass of this empirical formula and see if it is approximately 210. As you're working, I'm going to work through it as well. I want to get to the second and third eye clickers before the end of class today. So we check the molar mass. Okay, so on the board, I've calculated the molar mass of the empirical formula. So 13 times the molar mass of carbon, 18 times the molar mass of hydrogen, 2 times the molar mass of oxygen. Add that all together, and it's about 206 grams per mole. So that's just less than 210. So that means that the empirical formula that we determined is the molecular formula. So one molecule of ibuprofen contains 13 carbons, 18 hydrogens, and 2 oxygens. Like rounding up to 210 or?
It was 206.
Yeah, so if you're asked for the exact molar mass, then you would keep 4 sig figs. But in this case, we're just determining if it's a molecular formula or not. So it's okay to not have the correct sig figs there. Yeah. Good question though. Okay, so this is the molecular formula. Let's look at an example where our empirical formula is not the molecular formula. So the empirical formula of a molecule called hydrazine is NH2. its molecular mass, its molar mass of the actual molecule is 32.0 grams per mole. Now the question is, what is the molecular formula? So to determine this, we need to find the molar mass of the empirical formula. So the molar mass of NH2 I have the atomic molar mass of nitrogen, 14.01 grams per mole, plus 2 times the molar mass of hydrogen. So I have the molar mass of the empirical formula, 16.036 grams per mole. But the molar mass of the molecule is 32.0 grams per mole. So you might be able to see that if you multiply the empirical molar mass by 2, then you get 32 grams per mole, and that's the molecular molar mass. So that means we need to multiply the subscripts of NH2 by 2 to get the actual molecular formula. But let's write out that process. So we find N, which is a, actually I don't have a definition for N, but it's just the integer that we need to multiply the subscripts. So this would be the ratio of the molecular molar mass to the empirical molar mass. So 32 grams per mole over 16 grams per mole, that gives us an N is equal to 2. So then we multiply all the subscripts in the empirical formula by this factor of 2. So we would do N, where the subscript we assume 1 times 2, and then hydrogen in the empirical formula has a subscript of 2. In the molecular formula, we multiply that by 2. And this gives us the molecular formula N2H4. The next slide has all of these steps written out. I will go back to that slide in a moment. And then the next slide that's in yours and one additional question are the last 2 iClickers for today. So I will push these to your devices. We're essentially doing the same process. So you're given an empirical formula in the molar mass of the actual molecule and then determining what the molecular formula is based on that information. Okay, this will be the last thing we do today, so you're all set. Good to go. I'll keep this open for a few more minutes. Oh, we will start chapter 4 on Friday, I believe. So keep an eye out for an announcement. I'll have the PowerPoint ready tomorrow afternoon. Thank you.